this part in a separate audio. All right, so let me switch this to screen slideshow mode. Huh? There we go. All right, so again, tonight we have Rachel Shagat presenting on toys, the toy industry and the use of Six Sigma. So the toy industry is those regulated industries, much like healthcare and automotive and aerospace and defense, focused more on the consumer side of the economy. So just a quick reminder that if you are interested in enhancing your career or seeking a new job, or maybe looking for your first job, that if you log on to ASQ.org, they do have a tab there called Careers, and they have a pretty large database of job openings around the world actually, but you can toggle to your location. So I indeed put a filter on, and just in Arizona there are currently 26 jobs, ranging anywhere from a VP and Director of Quality to a quality engineer, quality technician, inspections. A lot of different titles and tasks and duties are in that career page of ASQ. Recently, ASQ conducted its first ever Women in Quality Symposium. Not sure how many of you had an opportunity to register and attend that virtual symposium. But there were 3 key takeaways, and I think this was broadcast out from ASQ, but I just thought I'd one more look at what some of the 3 takeaways were from that symposium, which particularly important for women in quality and work everywhere, to make sure that they build and use a network, actively mentor and sponsor other women in quality. And then the thought here is on intentional leadership that encourages diversity, empowers others, advocates for greater diversity, equity, and inclusion. And then very important to build your career and enhance your personal toolbox. So developing your own leadership and communication skills and tactics to be able to work through the obstacles and biases that women obviously face in the workforce today. Turning our attention to ASQ conferences, just a reminder that the Lean Six Sigma conference, which is traditionally held right here in our backyard at the Point Hilton Hotel, is coming up first week of March. It will be 100% virtual. You'll have a mix of live and pre-recorded sessions. So if you are interested in the Lean Six Sigma conference, I think registrations are now open, and you can pick and choose which session you want to attend. There are a number of live sessions and an even greater number of pre-recorded sessions that you can watch at your leisure. And one of the unique things we're going to try this year is conduct virtual tours. They're going to be live Gemba walks within several businesses here in the Phoenix area. So as the management team goes out to the production floor, we'll follow up and participate in a live Gemba walk. That should be very interesting. And so the traditional 1.5 day or 2.5 day conference is being expanded to 4 days. And with every day there'll be a keynote speaker, then different live topics, and again pre-recorded. And then in May we have the World Conference on Quality. It will be a hybrid combination of virtual and in-person for those of you perhaps where it's convenient to travel to Milwaukee. That's where this event will be held, much like this past year. If you can't get to Milwaukee, ASQ says they're going to be enabling what they call watch parties. So the individual sections can register for a watch party. So then members can our section members can join our section watch party. and you can participate in these live and pre-recorded sessions as well. More information will be coming up here in the near future on that. Turning attention to our own section, I want to thank everybody for your participation in our program meetings. You see by the numbers on the right-hand side, their participation has been growing these last several months. And just as important, if not more important, is your satisfaction level is consistently above last year's running average, which was 85%. So we're good. It's another Heather and Vic's hat. Our program chair has done an excellent job of finding speakers and topics of great interest to our members. We're getting close to the end of the year, so we're wrapping up the concepts we have to try to instill and create some excitement around My ASQ, where every month we have a drawing, people who create a new profile on My ASQ. So the winners in November were Alexandria Victoriano, Joshua Thompson, and Lincoln McFerrin. And hopefully Shruti, our My ASQ admin, has been in contact with you to offer you a $10 gift certificate, or you could choose to donate that to St. Mary's Food Bank. Unfortunately, we didn't have any new or participation in existing discussion topics. That's another part of My ASQ, kind of like LinkedIn or maybe Twitter, is you can post a discussion topic, and if you have questions, other peers and colleagues can participate, give you some suggestions or what they've seen, what's worked, what not worked. So we really highly encourage you to participate. I mean, that is the intent of My ASQ, is to create more networking and collaboration. And maybe you're getting tired of seeing this, but I feel it's my responsibility as your chair to keep you informed of what your leadership team is working on. So you can see back in November of last year, we put together our plan. These were our 12 priorities. Of course, that was before COVID hit, if you will recall. So in spite of COVID coming along in March, April timeframe, we have done, I think, an overall fantastic job in delivering on most of our strategic plans. The one we did have to delay, and we've delayed it till next year, it's on our 2021 plan, is to work on the placement process. That's dual role kind of, we're reevaluating what is our value proposition as far as offering a job board or career opportunities. You know, we're kind of competing with other well-established firms like LinkedIn, Indeed, and even ASQ headquarters. But so we want to take another look at that and see, well, what can we offer? How can we differentiate ourselves? Obviously focusing more on the Phoenix or Arizona area. But otherwise, the only two plans we have yet to complete, and they're both dark green, so they are very close to wrapping up, is a down deep and dirty market analysis of our membership, so we can look for market segments that we haven't served too well, and then new partnership agreements, offer new bodies of knowledge, or to expand on our body of knowledge. And I do want to recognize David Gibson, who's with us tonight, and Walter T. They were awarded 2 member leader recognition awards earlier this month. David, for his longtime commitment to the section. He's been our chair. He's now our immediate past chair. He's been serving the section for many, many years. And the other award goes to Walter T., who's our Sundial newsletter editor, who is stepping down after 17 years as our newsletter editor. So definitely want to wish Walter best of wishes in his retirement. And by the way, we are still looking for a new newsletter editor. So if this is something you might have some interest in, appreciate you sending me an email or voicemail or text. And then recognizing the fellows that we have in the section. There are eight of our members who have achieved fellow status. Fellow status is recognized after significant contributions to the society. And this is just an example of a certificate. But there are eight of us in the section so far. And if you're interested in possibly becoming a fellow, there are minimum requirements, and you can look that up on the ASQ website. Let me go back to participants. Maybe have a few more that's since joined, and I can mute all again. Let's see, I'll take care of it. Mute all. All right. Oops. So again, here's our leadership team for this year, 2021 coming up. You see most of our positions are filled. We do still have this need for a newsletter editor, and not as urgent, but down the road, once we start having face-to-face meetings again, we would like to have an on-site arrangements chair. This person helps make sure we're all set up and ready to roll, and so they take on-site registration, make sure we have the speaker gifts and random drawings ready to go, and then any other responsibilities we have. And then our newest member, our education chair, our current chair is stepping down. Chris Hermanette has done a great job for us, and taking over from Chris will be Pat Olstad. So welcome to the team, Pat. I know you're on the call tonight as well. So we have a pretty good sized leadership team working in unison to deliver value to our members. If you'd like to join the fun, again, please give me a call. All right, so that's the call for volunteers. So turning our attention now to the reason you're all here tonight, our guest speaker. Oh, man, how did that get messed up? Sorry, you're not talking about the best practice, are you, Rachel? That was last month. Oh, ignore that title. I don't know how that happened. So the topic for tonight is toying around with Six Sigma, and it's a look at the tools and practices you need within the toys and juvenile products market. It is a regulated industry in the consumer space. Rachel has worked 35 years in the area of quality. For the past 20 years, she's dedicated her work to ensuring consumer goods, primarily within the toy and juvenile products industry, are designed and manufactured to meet rigorous product safety and quality requirements. Rachel has worked at Fisher-Price, Tommy, Munchkin, prior to launching her own consulting business, Best Practice Quality, LLC. So in her previous life, she worked in aerospace for Moog and in automotive for Trico products. Throughout her career, Rachel's traveled extensively working with quality colleagues in 15 countries, including living in Ireland, where she installed and implemented ISO 9001. So the abstract of tonight's presentation is learning how Six Sigma is applied to the toy and juvenile products industry to build safe, quality tools, or toys. And oh, by the way, majority of those toys are manufactured overseas. So how do we assure that they're delivering the quality that our standards and expectations would dictate? So she's going to introduce some basic Six Sigma concepts, so it might be reviewed for many of you, but then she's going to demonstrate how some of those tools are used and modified to fit within the industry that is as unique as it is primarily set in Asia. Some of the tools she's going to introduce are 5S, Pareto, Fishbone, process capability, design of experiments, and Weibull analysis. So with that, I would like to turn it over to Rachel. And Rachel, I will make you the presenter so you can share your screen. All right. And
okay. So am I on?
Yes, you are, Rachel. Thank you.
Everybody can hear me and everybody can see my screen?
Well, I know I can see it.
Okay. All right. Well, welcome everybody to tonight's presentation. I just want to preface this by saying that this is a very entry-level presentation meant for students and next gens and people just kind of getting into the business. So it's more about the what, when, and where, and not about the how. And if you want to go to, thanks Ronald Tucker for letting me know that you can see our screen. If you want to go to the how, that'll be next presentation, or the Lean Six Sigma conference that's coming up is a great place to learn a lot more about the how. All right. So with that, this presentation is divided into 3 sections. First section is on Six Sigma and quality in toy and juvenile products industry, and with a little bit of feedback from a previous presentation, I was told to cut out a lot of that because it's dry and boring. Regulatory tends to be. So I did move quite a few of the slides for that section to the back. I call it, it's in the stocking stuffer section. And then we're going to move over to Six Sigma Basic Introduction and the DMAIC process. And finally, we're going to wrap up with a bunch of toys, Six Sigma toy box tools that we use within the industry. So the regulatory framework, I will go over some of these things, but like I said, I moved a lot of this to the back of the deck. And if you have any questions, you can always reach out to me to go more into depth. And I have a lot of links back there that you can go to as well. So the regulatory framework for the toy and juvenile product industry starts back in 1972 with the Consumer Product Safety Act. And that's the umbrella statute that created the Consumer Product Safety Commission, CPSC. And from that, there were the Code of Federal Regulations, 16 CFR 1500, and some of the regulations that were developed and tied to the toy and juvenile products industry. Fast forward to 2008, and you get the CPSIA, which is an improvement to the Consumer Product Safety Act. It was amended due to a whole slew of recalls that occurred in 2007. That's what really drove the changes in that. And there is additional slides in the back that tell you a little bit more about that. But what are the drivers to regulations in the toy and juvenile products industry? Well, it's injuries, deaths, recalls, penalties, product litigation. That's what drives pretty much all of the regulations. It's a lot of data on all of these areas. So just to share a couple of things that certainly had played a role in changing of the regulations over the years, leading to trying to use more and more Six Sigma tools, are things like the Fisher-Price first generation little people, which resulted in some deaths. And even though it met regulations then changed, and eventually you got to this guy over here on the right, who's X generation little people. Maybe not quite the last generation, because I do think they have, another generation or two, but you can definitely see that it grew in size due to choking incidents. You got a little green guy over here who ended up being recalled because of battery leakage problems with children, and a swimming product where the vinyl in the seat ripped and children died due to drowning. You have the Hasbro toy nails that went into a toy workbench. And these nails met all the regulatory requirements, and yet there were deaths involved because they had a unique shape. And nobody knew about this. This was an emerging hazard. Nobody knew about it. And it drove new changes to the toy standard. So the toy standard now incorporates dimensions that accommodate some of the uniqueness to these features. So the problem with these nails is that children fall on these nails, and they're just long enough, and they have a catch here so that if they impact the back of the throat, they actually get stuck back there and you can't get them out. And sadly, there were some pretty sad stories associated with some deaths with these nails. And the one that's probably the big emerging hazard that's been talked about over the last few years is magnets. So magnets, the price has dropped in the cost of magnets. So now you see magnets in everything. You see them not just in toys, but you see them in, purses, and just there's magnets everywhere because the price has dropped. And the problem with magnets is that for children, and even for teenagers, because teenagers also have used magnets for like fake body piercing, all right? What happens is that if it gets ingested, two magnets together can end up causing rippage in the lining of your intestines, and there's been deaths associated with it. So these are just some examples of the different, products that have gotten a lot of headlines due to deaths associated with them. This is kind of a lot going on in this slide, but I still wanted to show it because it's a good graphic on showing you what happened in 2008. You had 172 recalls, and 2019, you're down to 12. So there's been in the industry a lot of effort in changing regulations and getting the the product safety improved, and a lot of the recalls have dropped because of it. All right, so the toy safety standard goes around ASTM F963, which was voluntary up until the CPSIA 2008 enactment, which made it a mandatory standard. And even though it wasn't mandatory before 2008, all of the best practice toy companies, the large branded toy companies, they all met it, and most toy companies did meet ASTM F96, regardless of whether it was voluntary or mandatory. But anyways, all toys tend to have a base foundational set of requirements. So even though this toy standard is quite voluminous, it covers a lot of unique features in toys, pretty much every toy has to meet this set of requirements in performance, physical, mechanical, of tension, torque, compression, drop, and bite, simulating abuse and foreseeable abuse, and in labeling and warnings, and in analytical and chemical, and flammability is in here as well. Tension and torque. You can in other areas, but there are a little bit more nuances involved. So tension is the easiest way to introduce Six Sigma to a new group of people. So ASTM F963 has what they call compliance testing, and tension requirement is minimum of 15 pounds of force. If you grasp anything on a toy product and you apply that 15 pounds of force, then if something liberates off of there, you then test it for safety to make sure it's either not a small part or that it's a sharp, that it presents a sharp edge or a sharp point. So the 15 pounds of force is a compliance requirement, and due to the CPSIA, you had to send everybody has to send their products to an independent test lab, which is certified by the CPSC. And the problem is when they do these tests, they only test to the limit. So they'll test up to 15 pounds and stop the test. And you'll get a test report. It'll say pass or fail. The problem with that is that you never know where you are in relation to your design. Are you right on the borderline? The other problem is that samples are not like an inspection where you use AQL and you have statistically large sample sizes that work with a production lot. So instead, for testing purposes, the sample sizes are often a lot smaller. And so you have a small sample size and you're only testing to a compliance requirement, then the problem is that you are at a high risk of ending up with a potential recall situation, injury, etc. So the solution is that you really need to test to failure, at least during the design and development phase. By testing to failure, you can then calculate a statistic, and that allows you to then go on and know where your design is so that you can improve your design if need be, and also to look at what you need to do for process control and to determine whether you have a capable process. So there's a lot on this slide. I'm not going to go through all of it. I really wanted to stress that you must test beyond the standards, and you really need to test to failure. All right, so that's a really fast introduction into the regulatory world of toys. I really just brushed over it, but because this is Six Sigma, let's jump into what that's all about. So Six Sigma is data-driven problem-solving methodology. The focus is process variation. And if you reduce your process variation, if you make it narrow, then you're going to lower your defects. That's your goal. And so your aim is defect-free, 0 defects. So with Six Sigma, you can get to 99.999996% defect-free, which is 3.4 defects per million opportunities. Another way of looking at it visually is to look at your bell curve or a normal curve. Those of you who've had statistics, and I'm pretty sure most of you have, are familiar with this visual of the normal curve. And of course, you have your average and you have your standard deviations on each side. And if you go out 6 sigma, 6 standard deviations on each side, you end up with 99.99998%. This, I think it was 6% on the other one. But anyways, the point is that you basically have all of your population. So a really quick understanding of what I mean by that is if you were to measure all of women's heights, adult women's heights, you would find out that they fit under a normal curve, and that the average might be, and don't quote me, this is just an example, but let's say the average is 5'6". Your sigma out to the tail end on the left might be 4'6", and your sigma to the right might be 6'6". And so all women, adult women, 99.99998% of the women, all right, are going to be between the heights of 4'6" and 6'6". So that's using the visual with the normal curve to explain Six Sigma. And basically, again, if you get to minus 6 sigma plus 6 sigma, your defect rate is extremely low, and that's what you're going after. So how do you do that? Well, we use in the Six Sigma world a framework called DMAIC, and that stands for Define, Measure, Analyze, Improve, and Control. So you want to define your problem, map it out, map out the process. You want to measure the current process, and you want to collect data. Then you want to analyze it, determine root causes, brainstorm and implement solutions to improve it, and then you want to measure and monitor. And DMAIC is a circular process, a circular tool, because after you measure and monitor, you can also look to find new problems and go repeat this process. And what that'll do is you'll continually improve. So here's an example where a toy company up at the North Pole had a die-cast train, and the problem that they had was they had flash. So they used the DMAIC to help to solve their problem. So they identified their problem as flash that should be able to be removed by wet tumbling, but wasn't being removed sufficiently enough and causing a rework process, which was causing additional money and scrap. So if we look over to the right-hand side, you'll see a picture of a wet tumbling machine. You'll also see a picture of some different media that's used to knock off that flash. So you can use different types of media. So after they go to the define phase, they go to the measurement phase. In the measurement phase, they show both the process before degreasing, so the flash that's on the die cast before the going through the knocking down the flash. Then they show it in the red, the flash, and then they look at the green says that they really want to get a 30% improvement on this. So this is their measurement phase. They move over to their analyze phase, and they use a tool called a fishbone diagram here to determine what are the things that could be causing this excessive flash, not being knocked off during their wet tumbling process. And they identified two factors. They identified media ratio. So again, you have different types of media, and so they decided that they would have two levels of their media ratio, a 60-40 and a 40-60. And then they identified flash condition of paper flash, or what they called two types of flash, paper flash and hole shutoff flash. So they ran their experiment and they did an analysis, and they found out that in the analysis phase that these two factors were independent of each other. There was no crossover to them, but that one factor had more, between the levels, had more influence than the other factor did. And after they looked at that, they looked to see what they could do to address these issues and improve it. And they found that in improving their process, they were able to get a 35% improvement and reduce their manning, and they had also part saving in scraps. So they had a 35% improvement with 151K savings annually. In the control phase, they had standard operating procedures, and they assigned the R+, the person that had the responsibility, the main responsibility for doing the monitoring of those different areas of media cleaning, ball maintenance, flash type, and the checklist that they developed, the preventive checklist. And so this is just a very simplified example of using the DMAIC tool, but DMAIC is something that can be used for something that you're trying to solve a problem with. Once you've used the DMAIC, you start to use the Six Sigma tools within each of these phases. So at the back of the stocking stuffers, there's a couple of different slides that help you understand where the best tools are for using in these different phases of the DMAIC process. So with that, we're now going to jump into the toy box and look at some of the different tools that are used along the way. We're going to look at Pareto analysis on complaints and defects, fishbone diagram for root cause analysis, calculating CPKs for tension testing, using pre-control for injection molding, design of experiments for continuous improvement, and WIBO, which is a reliability statistic. We'll talk a little bit about that as well. So with Pareto analysis, it's a powerful root cause tool that you use to basically separate out the vital, what they call the vital few factors from the trivial many. And you use it to analyze frequency of problems and causes in a process. So when we look at Pareto analysis, we have on the left-hand side a graph, and it's called Failures in 2016. And along the bottom is your different failure types. On the left-hand side is the number of occurrences, and on the right-hand side is the percentage, so that if you added all of these failures types up, you would get 100%, right? So sometimes people use pie charts as well to look at some of this. But what Pareto does is that if you take and add these up sequentially, you will get to 100%. So if you look at 80% of your problems, it's really only dimensional deviation, corrosion, and short circuit. So if we work on these 20% of the issues, we'll solve 80% of our problems. And once we get done with that, we can rerun our Pareto analysis, and we'll find a new group of problems that are 20%. And it might not be these, because by that time, that could change. But basically, this is what the Pareto analysis tool does for you. It's a great visual. They also call it the 80-20 rule. But I want to point now to the right-hand side and the graph over here, because it's a little bit different, not quite as clean in terms of how you make your decisions. So in this graph, you have, it's showing 6 issues: missing parts, reliability out of warranty, information request, reliability warranty, safety concern, and performance. And basically here, so these are for at a call center and some of the issues there. And if you go with that rule of 80-20, now you've got 4 items you have to work on. It's not quite as, you know, it's a little bit more complicated now. Additionally, if you look over to the fifth one, and it's safety concerns, and those safety concerns could be critical issues that you may not want to ignore. So you may actually want to look at those first and just see. Additionally, you could have low-hanging fruit where it may be over to the right under performance, but it's an easy fix, and it gets you incremental improvement. So even though you have a Pareto analysis, it's a great visual, and it helps you to focus on the vital few. It doesn't mean that it's a standalone black and white tool that you have to follow the exact rule and you ignore the other indicators that are telling you to, that you need to maybe look deeper. There is a procedure on it under the ASQ link here. If you want to learn more about Pareto analysis, you can go there to that link. One more thing about Pareto analysis, when you're putting it together, this is a tabulation worksheet. And in this particular example, it's a toy end-of-line inspection. And so these are all the defects that are found at the end of the line. And what they do is they tabulate all these defects on a daily basis in this chart. And then at the end of the week, that's when they take their charting and move it to a Pareto analysis. So what you can see here, this one doesn't have the 100% on the right-hand side and the line adding up. You don't always have to do that to use a Pareto chart. If you want to just say we're going to look at the top 2 or the top 3 every time we're going at this, you can use that as a simplified tool, especially when it comes to communicating this tool in factories over in Asia where you have ESL issues and cultural issues. Sometimes simplifying a tool to work in that environment can work much better. So it might be better to say to your factory, just focus on the top 2, and then when you're done with that, or focus on the top 3, then rerun your chart. So what do you do now that you have your chart? How do you focus on the top 3? You have dirt, paint, missing parts. Well, your next thing you want to do is grab a fishbone diagram and work on your root cause analysis for those 3. So here's an example of a fishbone diagram on your left-hand side, and they call it fishbone diagram because it kind of looks like a fishbone. And over here is diameter out of spec, and that's at the head of the fish, and that's your problem. And in the factory, most of the time, you usually categorize your issues based on material, measurement, machine, method, environment, and employee, or sometimes they just call it people. Anyways, you do this because it's an easy way to group your issues. And you brainstorm what are the things that can cause your diameter out of specification. And you can see that you have your different types of potential issues. So for machine, it might be the wrong speed or the wrong feed rate or insufficient coolant. So your fishbone diagram, also called cause and effect, is a tool that's used. It's one of the 7 basic quality tools, and it helps you to find what your causes are, and it's best to be done in a group setting using brainstorming with a diverse group, by the way, because you really want the more diverse you have in your group setting, the more fluid flow of ideas you're going to get. There is a link here for Fishbone that helps you, and I believe that if you go to these links, you will also be given a template, and I'm pretty sure that one of these links will get you your template that you can use as well. Here's another example of Fishbone diagram. Part is produced wrong size. And here you can see it drills down a little further. So let's just look at measurement. Wrong size of the mold. Well, why? What caused the wrong size of the mold? Well, it could be a blueprint mistake, or it could be a production mistake. Now, you'll see that when you're doing this, you can keep doing whys, and they call that the 5 whys. So a fishbone diagram can be used to do the 5 whys. I've also seen it done on a template where you can just have a template that helps to drill you down to 5 whys. But the theory is that if you get to the 5th why, by that time you've definitely exhausted all of it and you're down to the root cause that you can go after to fix. So very simple and very useful tool. You can use it for anything, and it's used a lot in the toy and juvenile products industry for root cause analysis. So now I want to just take a break on the tools just to talk a little bit more about in-product development. So in-product development in the toy and juvenile industry, you start out with developing in early testing, and you do things like competitive testing, component testing. You may use design of experiments, which we'll talk about in a bit. And you do life and test failure, and we'll talk a little bit about WIBO analysis and in that area, life and test failure. And after you've gone through your development early testing, you also might do FMEAs. It was brought up, I think, earlier in the whiteboard, on the whiteboard with FMEAs, failure modes effects analysis. Those early testing will drive you then to get into your debug testing. And one of the things that you want to do when you're in the debug stage is you want to test a failure. We talked about it earlier. And when you test a failure, you want to tear down your tested product and look inside. You don't want to just get the failure, but you want to know how it failed. And you also, if you're doing redundant design, which is done a lot in the toy industry, you want to make sure that you're testing each redundant design independently. So what does that mean? So if you have, let's say, a welded part and also a solvent bonded part to contain a small part. So you have two pieces and they go together, one's welded, one's solvent bonded. You want to make sure that when you test them, you dismantle one. So you only test one welded, and you test the other one solvent bonded. And what you're going to do then is you're either going to do tension, most likely you're going to do a tension test, and you're going to do a drop test to see how they test out. You also consider things like doubling strategies. So sometimes you can't test a failure. And you may be able to test a failure, let's say, in the domestic design house or at a lab, but maybe in the factory you can't test a failure because that includes, like if you're doing a tension test, you might have to go over 100 pounds and they may not have that equipment. There's a slide in the back that shows you a bunch of equipment that's used for testing juvenile products and toys, and you'll see where the difference between a tension tester that might go to 50 pounds versus a tension tester that'll go to 500 pounds. So in order to calculate a statistic, you have to test a failure. But once you've been able to calculate that statistic, you may want to go to a strategy of doubling and determining a margin of safety that would say, instead of 15 pounds, I know that I should be able to achieve over 40 pounds. So I want everything to be tested to at least 40 pounds. You also want to consider continuous life testing. So continuous life testing means that because you don't have a lot of products and often you don't always have a lot of equipment, you might want to put a product on a life tester, like for instance, a product that had wheels on it, and put it on a belt so that it's running life testing. And when it fails, you take that off, you record your information, you throw another product on it. And you run that continuous life testing throughout the life of the product. Why? Because you can continually get new information that can tell you about the cycle testing and the failures. So it's a good strategy to use. And at this point, you may want to start looking at calculating CPK. Again, to calculate CPK, and we'll talk about it in a little bit, you need to be able to test a failure. Once you go through your debug, then you go to test validate, which is the FEP stands for Final Engineering Pilot Testing, and that validates your design. And then you want to go to pre-production, and that's going to validate your process. So in process validation, you want to make sure that that's when you look to determine your process capability and what you're going to do to implement process control. Here's where you also will use pre-control. And we'll talk a little bit more about pre-control later on, but pre-control is a tool that's used to help reduce variation and keep the process centered. And a lot of times there's different people and different groups that either believe in pre-control or don't, but it definitely has been used in the toy industry with good results. All right, now we're going to look at CPK index. So, the capability index is, you'll see people talk about CP and CPK. And CP means it's the capability of a process. So if you look in the center here with the graph, you see CP equals 1. And that means that your process and the normal curve, is touching the lower spec limit and the upper spec limit. So your capability is at 1. If you reduce your variation, all right, and you're holding center on your mean, then your capability can go up to 2. So that's your process. CPK is a calculation that allows you to correct for centering. So if you look to the CP equals 2, if you were to shift that to the left or right, that process curve, your CP is going to drop down because it's not centered anymore. Or it'll drop down at CPK, and so the CPK helps you to correct for the off-centering of the process. So you have a statistic that you calculate. There's your formulas in the center as to how you calculate those. And on the right, it shows you what your sigma level is and your defect level is for your different CP numbers. So if you have a 1.0, it's plus or minus 3 sigma, and your defect level is 0.13%. And at 2.0, it's plus or minus 6 sigma, and your defect level is 2 parts per billion. So in calculating your CPK, so if you're, let's use the 15 pounds again, if you're testing a toy and you're doing a pull test to see if it'll liberate a small part off of a graspable section of the toy, you're going to calculate your number to whatever it fails at. And that's, you're going to calculate an average, and you're going to calculate your standard deviations, and you're going to be able to, with those 2 data points, be able to calculate your capability. So here, I just want to point out that a CPK of 1.33 is typical acceptance for a process that's capable and can meet your spec limits, right? And in some industries, 1.33 would not be enough. And for critical to safety, 1.33 might not be enough, even the toy and juvenile industry. So it also depends on how something fails, as determines where you're comfortable with on your CPK index. And so when I worked in the automotive industry way back in a few decades back at Trico Products, Ford came in and with their Q1 program and said you have to put statistical process control on everything, and you have to calculate your capability, and you have to have a CPK of 2.0 or better. And so they had us put X bar and R charts in and do our capability studies, and they wanted 2.0. And at that time, we had a process that was at CPK was at 10.0, and Ford had wanted us to use this tool. It was a measurement tool, and it was ridiculous. We didn't need to use it because the requirements didn't, were tight. The process was tight, and so I was able to get Ford to remove that from their control plan by doing a capability study and showing them that the CPK was 10, and so we didn't have to go and basically dust this tool off every time Ford came in to do their tours and show them that we were using a tool, because we weren't using it because we didn't need to use it. And that's just an example of in the factory what happens. So over on the right-hand side, you can see that there's different graphs, different bell curves showing you different calculations for your CP and your CPK. Shows you how they differ. So if you go to B, you'll see that even though you have a very narrow variation, all right, and you have a CP calculation of 2.25, if you calculate your CPK, it's only 1.0. Why? Because it's touching the spec limit on the lower side. And if you drop down to D, you can see that that same bell curve, if you center it, will bring you back up to, a CPK of 5.0. So that's a little bit more about it. There's also a link again that you can go to learn more about capability indexes. It's a good link. We'll give you some more information. I have a couple more graphs on the CP versus CPK that I thought were useful for visually just demonstrating what it looks like if you're less than 1, which isn't any good for your CP, or if you're greater than 1. So in this case, this is a nice graph because it shows you your bell curve and how you're outside of your limits. And it also shows on the side where your CP index is, which is between 0.7 and 0.8. So it shows you the relationship. And if you get it to 1.0, this is what it looks like. And then if you move over to your right-hand side and you reduce your variation further, get your CP up to 1.2, this is what it would look like. So I like the graphic on this to help demonstrate what the result is when you reduce your variation. That was with CP. Now if you look at CPK, you get the same thing. On your left, you'll get your what it would look like if you're out of spec, and your CPK calculates to under 0.4, and you have it on the left-hand side or the right-hand side. And it shows you what it looks like at calculated at 1.0. So you can be a little bit narrower, but you'd be shifted to the lower limit or the upper limit on that graph. And so you have a little bit of room here because of your variation being slightly narrow, but you still only have a CPK of 1.0, so that's not good. And then reducing variation is going to get you to the and centering. So you want to reduce your variation and you want to center, and that'll get you up to 1.2 CPK. So that's a really quick introduction into CP versus CPK. Here's an example of an application with tension testing. So you had a wood train set. It had magnets that connect cars together, and the design was to drive this nail through the center hole of the magnet into the wood. And the problem is that after abuse testing, you had small part liberation. And of course, it was also not just a small part, but it was a magnet as well. So you had two problems. You had choking, and you had the hazard of a magnet. And so there was an analysis done to identify the variables that you had. So you had variables in your wood density and in your moisture content. You had variables in your nail diameter and length. You had variable in your pressing operation. A CPK study, a capability study, was performed, and they determined that the variation problem was in the wood, and there was nothing they could do about that. And so they had to redesign the toy, even though they wanted it to be an all-wood toy. They did have to add some plastic to it to contain the nail. And then they had a redundant system to contain the plastic component with the nail and the magnet inside. I have this graph over here, even though the application here was for a one-sided. That means only the lower spec limit was what you cared about. I just like the graphic and how it shows your statistic on each side of below spec product and above spec product. But in this particular example, and then the next one I talk about, and pretty much for most of the toy industry, you're talking about a one-sided CPK. So here's a second one. It just shows you how you can calculate your CPK as X bar minus 15 is greater than 3 sigma. And if you were going to tell your factory a spec, you could say X bar minus 3 sigma must be greater than 15. And now factory, you must calculate your X bar and your sigma in order to do your measurements. And again, going back to the factories can't always do that. So in some cases, you then have to do your study, determine where your numbers are, and then give them that minimum margin of safety number, that whatever that might be. So let's look at these scenarios over here on the right-hand side where you have A, B, C, and D. So you had 7 parts that you tested, and an A, these are what you polled at, your forces that you polled at, and you ended up with an average of 29.9 with a standard deviation of 2.54. Your lower spec limit's 15, and your CPK is 1.95. So not quite 2.0, but not too bad. And you can see when you come down here what your defect rate is and your quality level at average minus your 3, 4, 5, and 6 sigma levels. So the reason why I show this is because in the toy industry and the juvenile products industry, one of the things that you're going to give your factory is you may say, well, for this particular product, it has a magnet in it, or I'm really concerned about this design. So it's not going to be X bar minus 3 sigma. It has to be greater than 15. You may tell your factory it has to be X bar minus 4 sigma or 5 sigma. So you have to determine by risk and evaluation of when you did test a failure in the design stage and how your item failed as to what your level is going to be. What is your quality level going to be? B just shows, a different set of numbers is going to give you different average standard deviation, and now your CPKs drop down to 1.75. And now if you look at your quality levels, you're starting to go into the yellow at 5 standard deviations, but you're still looking good at 4 standard, the average minus 4 standard deviations, and you're at 60 parts per million. And that would probably be pretty good for a lot of the toy industry. But again, we always have to look at the failure, how it failed, and what are your risks. As you move down in the numbers, you can see how it just goes further to the risk point where you're actually not going to run because you're going to have to, do a redesign effort. Even though you're above your 15 pounds, you still have to do something about it. So that's another example of using CPK and setting your standards in the toy industry. All right, pre-control. So pre-control is used to monitor a process. It's really simple to use, and that's why people like it, especially, again, when you're talking to factories and you're trying to simplify things. Provides visual reference, and there's a pre-control chart over here where you can see your upper spec limit, your lower spec limit, and your center line. So what you do is you say 50% of, 25 on each percent of your center line is in the green, 25% past that is in the yellow. That equals 100%. And if you come out of spec, then you're in the red. There's a few rules that go with this, and how you start out is, let's say you have an injection molding machine, and you're setting it up, and you're telling the setup guy that you need to run, 5 in the sequential parts in the green, and once you do that, you can start sampling. And then you have some simple rules that say if you have one sample, you sample 2 pieces. If one is in the yellow and one is in the green, then you do this. If 2 are in the yellow, then you do the adjustment. If they're in the red, you do the adjustment, and you go on like that. So the rules are very similar to using, for those of you that are familiar with X bar and R charts, it's similar to that, but there's a lot more rules involved in X bar and R charts, so they get a little more complicated when you're dealing with factories, especially overseas, to utilize X bar and R charts. So the pre-control chart makes it easier. There are some people, though, that don't believe in pre-control charts, and so you have 3 links here, and you can go and see for yourself and make your own judgments as to whether pre-control chart is something that is a tool that you want to use or not. But it really is useful in injection molding setups to dial your parameters in to run. Okay, finally, well, now we have 2 more actually. So next one is design of experiments. So design of experiments is really a powerful analytical tool that allows you to look at multiple input factors and changing them at the same time. So often in testing that you'll use what they call one factor at a time, where you only change one variable at a time, or they also call it cost. And Bob, if you get a chance, can you remute everybody for me, please? One factor at a time or cost are the same things. They're just 2 different acronyms, but they mean the same thing. Cost, I think, is changing one step at a time. So if you look at an injection molding machine for plastic parts, you have usually factors like temperature, time, and pressure. And so in one factor at a time or cost approach, you might change your temperature and then run some parts, and then change your temperature again and run some parts. if you don't run a design of experiment, you can make changes all at once. And what you do is you tend to change by picking a high and a low for each of your factor. And often you'll put your center point in there as well. And so you might have high temperature, lower temperature, and a neutral or a center temperature, a higher pressure, a lower pressure, center pressure, and more time, less time, and a center point on that. And by running all of the factors at once, it allows you not only to see how certain factors affect the outcome, but it also allows you to see how they affect each other. So there's these inter effects, and that's the beauty of design of experiments. So design of experiments can get quite complicated, and there's a lot of statistical packages out there that can help you run a design of experiment. What I'm presenting here is just the intro into thinking about using a design of experiment. And once you think, oh, this might be a good opportunity to do a design of experiments, that's when it's time to learn more about it, go get help to be able to do that. But design of experiments can be very, very useful to help you both in designing a new product, but it also can be very useful on the back end when you have failures and you want to determine causes for failures. You can also use design of experiments. So it helps answer questions, key factors of the process, and it helps you determine your key, your main, and your interactive effects in the process, and allows you to optimize then your design. So here's an example. It's a very simple example. So here's this North Pole toy company that received customer complaints about a game it had. And this game was getting a lot of returns. And it was a game that did auto shuffling. And the shuffling feature was not working properly. And so engineering looked at it, and they decided to redesign the card exit slot to open it up. And they also wanted to do some cost savings. So they decided to change the motor as well. They were going to change the motor. And quality came along and said, well, whoa, wait a second. Let's do a design experiment on this. And so they had two factors. They had the slot size and the motor. And so they did a 4 factorial design. And so through that design, they ended up with a result. And their result determined that the slot opening up, which is kind of logical, but it's still good to run your design. But the slot that they opened it up to did, in fact, fix the problem. However, those samples that had the new slot with the new motor, right, didn't actually fix the problem. And so if they had allowed engineering to go through and do their cost-cutting exercise, they would have still had complaints. And so they were able to say, no, you can't change the motor because not the way you have it, currently wanting to change, because you're not going to eliminate the issues. So very simple example of a designed experiment and how that works. And now WIBO analysis. So WIBO is a tool used in reliability, and it basically is used it can help you determine sample size and determine things like what life cycle settings to have, and it gives you the sense of, helps you to determine a probability so that you can get comfort in knowing that you have a high reliability on a specific design. So in the toy industry, it's used a lot it can be used a lot on electronics, but in the juvenile products industry, there's a lot of critical components. And so it's a good tool for predicting reliability on critical components. So if you're familiar, or if you're not, this is a bathtub, what they call the bathtub curve, because it looks like a bathtub. And it shows the statistic under less than 1, so the failure rate less than 1, means that you have early life failures. And early life failures mean that you have failures that tend to be process-related failures often. In electronics, a lot of times, they do burn-in to eliminate some of those early life failures before they ship a product, because there's just the probability that there's going to be some process-related values, often dealing with things like soldering and et cetera. And in your useful life, where your statistic is equal to 1, your failure rate, that's just random values. And on your wear out side of the curve, where it's greater than 1, that's where it's design related. And often you make warranty decisions based on this. And you know, whether you if you're getting wear out failures, you may decide, well, it's costing us money, so from a warranty perspective, and now we may need to change our components or change our warranty program. So when you're doing WIBO analysis, you do you use logarithmic paper, and so this graph just shows you that you have 3 straight lines. The red one is for failure rates under 1, which are early life. You have the green line, which is failures greater than 1, which are wear out, and you have the blue line, which is random failures. And when you're looking at your WIBO analysis, often if you have certain, depending on how your plot is, you can determine whether you have multiple failure causes with your failures. So here's an example of a use of WIBO analysis in the toy industry. And basically, buckles are used with child care products in all kinds of different settings. They're used for high chairs and carriers and car seats, and anywhere where you need to use a restraint system. And so buckles are considered critical components. And in this particular example, there needed to be a reliability test developed, and they worked with the lab to replicate actual use and come up with a realistic lab test. And they needed to test a failure. They couldn't just test up to a projected number of cycles because that wouldn't allow them to give them the confidence that they needed for this component. So samples were a limiting factor, but the WIBO analysis did help to determine their sample size. And I think for this study, it was probably sample size of 12, I think was what they used. And the WIBO analysis determines then what your mean time between failure is. And you calculate it. In this example, it was 24K cycles. And so all samples, must be tested to failure in order to be able to get your calculations. And the WIBO plot expectations was data along a straight line, which they had. And there was only one failure mode, so it was a simplified analysis. And they were able to determine that if they met the minimum cycles of 24K cycles, that they had 99% reliability on their buckle with 95% confidence level. So I'm sorry I kind of went through these very fast, but I just wanted to really introduce them to get you to think about when you might be able to use a tool like this if you haven't. And if you want additional information, you can reach out to me. But this is just shows you the stages for these tools of where you might want to use them. You can basically use these tools at any stage, but in the examples that I showed you, and often where it's used in toy and juvenile, are in like either new product development for design of experiments or CPK, pre-control, manufacturing, and post-market surveillance. You do a lot in manufacturing and post-market surveillance using your Pareto and Fishbone. All these toys that I show you are not toys that have anything to do with the examples that I showed you. I just picked them because I thought they were either cute for the presentation, or they had iconic representations, or like the potato head. We always associate Pareto with the potato head. So that was the only reason. So there's no other reason why these toys are here. Just making that disclaimer. Please, if you have any questions, I know this is a long presentation, and it's again about the what, when, and the where to use the tool. But if you have any questions, please, you can send them to me. You can email me, and I'll be glad to answer any of those. Also, just wanted to give acknowledgments to those people and links that I used within this presentation. And then in the back of your handouts, you should have a Six Sigma stocking stuffers where I'm just going to race through this, but you have a lot of information here. You also have links, and you have things I didn't talk about, other tools besides DMAIC, and just to touch on Lean Six Sigma, that if you're going to start down the lean path, the best place to start is 5S. That's always the best place to start because you get a lot of wins with the early successes, which breed follow-on success, and a 5S program, project is a way to get early successes. And with that, regulatory information is here. And that is the end of my presentation.
Okay, well, thank you, Rachel. Does anybody have any questions? If you could either unmute yourself, raise your hand, and I'll unmute you, or there is a Q&A box. It's an option along next to chat. So to the far right, there's a down caret symbol. And if you click on that, you can pull up the Q&A box, and then you can type in any questions. So anybody have any comments for Rachel and her presentation on Six Sigma in the toy industry? Well, not hearing or seeing any, I will take control and share my screen once again. And all right. So just to wrap up again, Rachel, thank you very much for your presentation on quality in the toy industry. Very topical this time of year. And let me turn my camera on. How do I do that here? Participants, camera. There we go. You can see me. Just for a reminder, if you would please complete the evaluation survey when you receive it when you see it via email from John Lindland. And again, as always, if you have any suggestions for improvements or suggestions for future topics, as well as those that we captured this evening during the networking session, please do give us some tips and advice. Coming up in January, we are hoping to have two different types of presentations. The December webinar that I had mentioned, co-sponsored by the Statistics Division of ASQ, was moved to January. That was their call. They just figured with the holiday season and it's already hectic enough that they would move it to November. We do not yet have a date for that, but I have been told it will be in January. And looking back on their My ASQ community site, they have a whole string of webinars that they have recorded that are available if you would be interested in watching them. And their webinars are generally presented around 9 in the morning, Mountain Standard Time. So if you'd like to, when you do see the announcement, you can register, and it is a free 1-hour webinar. Usually has a presentation you can download as well. And then our regular monthly program is back to the second Thursday of the month. So January 14th, we have a presentation on design thinking to drive employee experience. And our speaker will be Mukesh Agarwal. And then coming up in February, we have a program meeting on compassionate leadership by two speakers from Amazon. So hopefully you'll find those interesting. Without further ado, Koki and Gumby say thank you very much for the presentation and hope you have a safe, happy holiday season. Thank you, everybody.